large university campus, thousands of students and dozens of courses, all existing at once. If you try to map out who is taking what, you end up with a chaotic, tangled web of isolated interactions. To make sense of this, mathematicians use a binary relation, a defining link between items in different sets. If a student, X, is enrolled in a course, Y, we write X, capital R, Y. The student relates to the course. But a raw web of binary relations is still too messy for an algorithm to process. To transform this into something useful, we have to define the difference between ranking items in a sequence and sorting them into groups. By applying specific, rigid mathematical constraints to these raw links, we can force chaotic data to behave according to predictable rules. To build that structure, mathematicians test every individual connection against a checklist of 4 logical properties. The first property is reflexive. This means that every single item in the set must relate to itself. Next is transitive. Think of this as the chain reaction rule. If item A connects to item B and item B connects to item C, then A must automatically connect to C. The third property is symmetric. This acts as an equal two-way street. A connection from A to B guarantees a return connection from B to A. And finally, antisymmetric. This enforces a strict one-way street. If A connects to B, B cannot connect back to A unless they are the exact same item. By treating these 4 properties like toggle switches, computer scientists build the different data architectures required for digital tasks. If the goal is to rank data in a specific order, we rely on the logic of a hierarchy. This structure is called a partial order. To create it, we toggle on 3 specific properties. It must be reflexive, transitive, and crucially, antisymmetric. In a less than or equal to relation, the antisymmetric property acts like gravity. It forces the numbers to flow in one unchangeable direction without ever looping back, ensuring that if 1 is less than 2, 2 can never be less than 1. At the same time, the transitive property ensures the entire vertical chain holds together. It allows the system to instantly know that 1 is also less than 3 without needing to run a separate comparison. Without antisymmetry to block those two-way loops, our data would fall into logical paradoxes, making it impossible to establish a reliable leaderboard or search ranking. Curious, shifting tone. But categorization requires a different set of rules. To group items by similarity, we need a flat structure rather than a ladder. This is an equivalence relation. By swapping the antisymmetric rule for the symmetric rule, the entire behavior of the data shifts. In this model, symmetry has removed that top-down gravity. Data points that share a common trait now link equally to one another, creating a peer-to-peer structure instead of a ranking. This peer-to-peer symmetry is the mathematical requirement for pure categorization. It allows items to be identified as equivalent without one being superior to the other. This grouping leads to a systematic consequence. When you establish an equivalence relation, it automatically generates a partition in the data. These clusters form boundaries called equivalence classes, dividing the dataset into distinct, non-overlapping zones. A partition ensures every item is placed securely into a defined bucket. Nothing is left floating in the void between categories. Macroscopic order emerges from these microscopic rules. We take the chaos of the university campus and, through 3 properties, arrive at a perfectly sorted directory. This logical framework provides the structural rules for our digital interactions. When a streaming service sorts its library by genre, it uses partitioning to ensure songs are filed correctly, never drifting between unrelated categories. When a search engine displays results in sequence, it follows the gravity of a partial order to prevent ranking paradoxes. These constraints on how items relate are the underlying grammar that allows the modern digital age to be legible and organized.